Inside a precision engineering shop in the north of England, a machinist clamped a single human hair into a 5-axis milling machine and drilled 5 holes through it in a straight row without snapping it. A human hair measures about 0.09 millimeters across. The machine that drilled it holds position to within 0.3 microns, roughly 300 times finer than the hair itself. On this list, that machine only ranks number 4. These are the 15 most precise milling machines ever built. Between them, they cut the mirror segments of the James Webb Space Telescope, the mold cores behind the lenses in your phone, and metal surfaces smoother than a wavelength of light. And at the top of the ranking sits a machine whose axes move in steps of 0.1 nanometers, a machine so sensitive that for years, Japan would not let it leave the country. You are watching Trade Archive. If you want the machines behind the modern world, like this video and subscribe before the countdown begins. The ranking runs on accuracy, repeatability, and what each machine proves on finished metal, not on the resolution numbers printed in a brochure. The builder at number 1 came closer than anyone to eliminating friction itself. Number 15. The Mitsui Seiki HS6A. In September 2003, Axis Technologies needed to machine the primary mirror segments of the James Webb Space Telescope, billets of beryllium weighing 750 pounds and costing about $500,000 apiece, and it chose a Japanese builder few outside aerospace could name. Mitsui Seiki assembles its machines by hand in a temperature-controlled factory in Kawajima, Japan, on lead times that stretch to 6 or 7 months, and 77% of its international sales go to aerospace customers. 8 of its HS6A horizontal machining centers took on the telescope work. Scott Walker, then president of Mitsui Seiki USA, described the geometry plainly. The axes run straight to 2 microns, and perpendicularity holds within 3 microns across a full meter of travel. For a machine that size, moving that much iron through that much space, those numbers border on unreasonable. The same company builds jig mills that position and repeat within 1 micron, carrying a thermal compensation system called MAMS that reads sensors on the faceplate and inside the spindle, cutting temperature-driven displacement by 60% and thermal growth in the z-axis by 30%, and mold makers trust those machines for bores held inside 5 microns for location, roundness, perpendicularity, and straightness at once. On the largest models, that 5-micron pitch accuracy holds even between holes spaced far apart across the table, which is the harder problem, because error accumulates with distance. The telescope's primary mirror carries 18 hexagonal segments, and the beryllium behind them passed across those 8 machines. Today, the finished mirrors sit 1 million miles from Earth, unfolded in the cold and collecting light from the early universe. Every image the Webb telescope returns passes through metal shaped on this machine. And this is the floor of the list. Number 14. The Sodic UX650L. Sodic decided decades ago that purchased motion would never be precise enough, so the company developed its own linear motors, flat, contactless drives with no ball screw, no backlash, and no friction to overcome at reversal. On the UX650L, those motors carry a spindle hung from a gate-type double column, a symmetric bridge that spreads heat evenly instead of leaning with it, and thermal displacement at the spindle holds to about 3 microns. Ceramic components inside the spindle resist heat growth. The mating surfaces of the castings are scraped flat by hand. Linear scales report position to 5 decimal places of a millimeter. Mold shops run this machine to mill graphite electrodes and to cut hardened die steel directly, pulling finished cavities off the table so the polishing bench sits idle. On workpieces more than 1 meter long, it holds accuracy around 30 microns. The bridge itself is heavy cast iron, poured that way on purpose, while the newest versions carry carbon fiber reinforced tables to strip mass from the parts that move. And in 2025, Sodic extended the line with a 5-axis model. This is the machine that turned high-speed milling from a roughing trick into a precision discipline, and it sets up everything above it. Number 13. The Willemin-Macadel 508 MT2. The Swiss watch industry demands parts that combine turning, milling, and drilling in geometries no simple machine can reach, and the 508 MT2 from Willemin-Macadel was built to finish them in a single clamping. It is a 6-axis mill-turn machining center. Bar stock enters, and a finished watch component or a titanium medical implant comes out, untouched between operations. Linear motors drive every linear axis and torque motors drive the rotaries, so nothing in the drivetrain wears and nothing reverses through backlash. The milling spindle turns at up to 42,000 revolutions per minute on an HSKE 40 interface, and the axes accelerate at 10 meters per second squared, so the machine holds micron-level accuracy at production pace rather than in a laboratory crawl. A thermal stabilization system the company calls DTS manages the heat sources inside the structure, and the vertical axis is weight compensated, so its drives fight cutting forces instead of gravity. Larger versions of the platform coordinate as many as 9 axes at once, and for the smallest work the company builds the 701S2, a parallel kinematic micro-machining center whose delta arm arrangement positions the spindle with almost no moving mass at all. Willemin-Macadel sells into watchmaking, jewelry, medical, and aerospace micromechanics, industries where a component the size of a fingernail carries features a human eye cannot resolve. The Swiss did not build this machine to chase records. They built it because their national industry cannot exist without it, and that pragmatism is exactly why it makes the list. Number 12. The Fraunhofer IPT Compact Micro Machine. Not every machine in this ranking came out of a factory. Researchers at the Fraunhofer Institute for Production Technology in Aachen, Germany, attacked precision from the opposite direction of everyone else here. Instead of adding mass, they removed it. Their compact micro-milling machines shrink the entire structural loop, the physical path from tooltip through spindle, column, base, and table back to the workpiece, on the logic that a shorter loop deforms less, weighs less, and holds less heat. The result is a research machine that achieves spatial positioning accuracy below 3 microns across all 5 axes, a volumetric figure covering the full working envelope, not a single flattering axis. That distinction matters. A machine can post a brilliant number on one axis and still stack errors into a part when all 5 move together. The Aachen work proved that a machine does not need to weigh 10 tons to be accurate, and the thinking behind it, minimum mass, minimum loop, maximum stiffness per kilogram, echoes through the commercial micromills higher on this list. Consider it the laboratory ancestor of the machines you are about to meet. Number 11. The Primacon P40cc. Primacon has built micro-machining centers accurate to better than 0.001 millimeters for more than 30 years, and the P40cc is the current expression of that lineage, an automated 5-axis micro-precision milling cell. Water circulates through the machine bed and through the motors themselves, pulling heat out of the structure before it can move a single micron of geometry. The axis arrangement is designed to minimize compensating movements. Torque motors drive the rotary axes directly, and a Heidenhain TNC 640 runs the show. The company states accuracy on the workpiece below 1 micron, and documented customer work has held tolerances under 0.5 microns with high surface quality. The P40cc also does something no other machine here does. It performs guilloche, the fine decorative engraving on luxury watch dials, alongside conventional micro-milling on the same platform. Watch dials, jewelry, micro-optic mold inserts, and high-performance components all come off this machine, and 0.5 micron on a finished workpiece is the kind of number that puts a small German builder ahead of giants. Primacon knows exactly where that class boundary sits, because it also sells a deliberately simpler machine, the in-house 5X, specified at plus or minus 10 microns. Same company, 20 times looser, a fraction of the cost, and an honest admission of what the last half micron is worth. Most viewers will never have heard this name. The people who buy these machines prefer it that way. Number 10. The Rotors RXP series. Rotors builds high-speed, 3-axis and 5-axis machining centers where friction has been engineered out of existence. Linear direct drives move every axis with no contact and no wear. Glass scales read position in 5 nanometer steps, and the control recalculates the machine's position 32,000 times every second. Spindles run from 50,000 to 120,000 revolutions per minute. The frame is cast from polymer composite, a material that swallows vibration instead of transmitting it, and a thermal management system called pre-SciTemp, offered in 3 stages of escalating seriousness, holds the machine's precision even when the workshop around it drifts. The newest RPT machines add a guideway concept called nanotol, built for running accuracy at the nanometer level, and the platforms integrate jig grinding, so a hardened part can be milled and ground to final size in one setup. The results show on the part: reliable submicron accuracy in both geometry and finish, with surface roughness reaching single-digit nanometers. And the on-machine measurement is accurate enough that the packaging molds specialist Alpla stopped sending finished parts to a separate coordinate measuring machine because the numbers coming off the rotors matched it. Mold and die shops, aerospace suppliers, and medical manufacturers run these machines hard, around the clock, in serial production. The motorsport and aerospace machinist CRP Mechanica runs them, and the cutting toolmaker Mapal uses them to prove out its own tooling, which is the industrial equivalent of a character reference. Pay attention to that detail, because it separates this half of the list from the last. From here on, submicron is not a demonstration. It is a Tuesday. Number 9. The Makino IQ300. Makino built the IQ300 around a conviction that the spindle is where precision goes to die, and then refused to let it. The 45,000 revolutions per minute spindle is cooled at its core, under its bearing races, and through its jacket at once, a triple circuit that all but eliminates thermal growth, deflection, and vibration at the tool. Linear motor axes ride on scale feedback reading in 5 nanometer increments. Positioning accuracy lands around 0.5 microns, and the machine sits on a vibration-damping base inside an enclosure with actively managed air temperature. The control runs Makino's SGI.5 software, which reads far ahead through the thousands of tiny program blocks that define a micromold surface and moves the machine smoothly through them, instead of stuttering block to block. Runout at the spindle interface stays below 1 micron. A hybrid system measures tool length automatically to strip setup error out of the process, and for larger dies, Makino scaled the same architecture into the IQ500. Shops use the IQ300 to mill tungsten carbide stamping dies with ball-end mills as small as 150 microns in diameter, and to cut the mold tooling behind LEDs and precision optics. Carbide is the material that grinds other tools away. This machine carves it with a cutter thinner than 2 human hairs and holds the result to half a micron. If this countdown has earned it, give the video a like and subscribe to Trade Archive, because the top half of this list is where machining stops looking like machining. There is a hierarchy hidden inside this ranking, and it runs through the bearings. The lower entries replaced ball screws with linear motors to kill backlash, but their axes still roll on hardened steel elements, and rolling steel carries its own microscopic noise. The machines from here upward abandon contact entirely. Some float their axes on pressurized air, frictionless and silent, ideal where cutting forces stay tiny. The most extreme float them on pressurized oil, hydrostatic films that combine zero friction with brutal stiffness and damping, the same principle behind the finest grinding machines ever built. Once nothing touches, nothing wears, and the geometry a machine ships with is the geometry it dies with. The next builder on the list floats its machines on air. Number 8. The Kugler Microgantry Nano. Kugler has built ultra-precision machines since 1983, and the microgantry Nano is its air-bearing micro-machining center, available in 3- and 5-axis versions. The axes ride on aerostatic bearings, meaning the moving parts of this machine never touch the stationary ones. They float on a film of air, with no friction, no wear, and no mechanical noise to print into the surface. The base is a block of fine-grained granite, chosen for thermal and mechanical stability, and the air film itself damps vibration passively. With monocrystalline diamond tools, the machine produces optical surfaces, metal mirrors, and precision V-grooves. And Kugler's ultra-precision work reaches flatness of 100 nanometers across 100 millimeters. Research institutes including Fraunhofer YLT and Han Schickard run Kugler machines for laser optics work, which tells you the customer profile. These are not mold shops chasing cycle times, they are physicists who need a mirror. A milling machine that finishes a surface to within a wavelength of visible light has left ordinary manufacturing behind, and Kugler is only halfway done on this list. Number 7. The Kugler MicroMaster. Same house, different physics. Where the microgantry floats on air, the MicroMaster runs on oil, hydrostatic bearings that trade the weightless touch of aerostatics for enormous stiffness and damping, with travels reaching 500 millimeters. The granite base remains. The diamond tooling remains. What changes is authority, because an oil film under pressure resists cutting forces that would push an air-bearing machine off its line. Kugler quotes turned and milled components accurate to well below 1 micron, optical surfaces with roughness below a single nanometer, and shape accuracy better than the wavelength of light. High-performance laser optics, metal mirrors, and mold inserts for optical parts come off this platform, finished, with no polishing step to follow, and Kugler pairs the machines with coordinated cleaning and metrology stations, because at this level, a fingerprint is a form error. Kugler is one of only 2 builders to place 2 machines in this ranking, and the fact that a company most machinists have never encountered occupies both of these slots says something uncomfortable about how quietly the ultra-precision world operates. The other builder with 2 machines on this list is coming, and its numbers are harder still. Number 6. The Yazda YMC430. Yazda builds the YMC430 Micro-Center the old way and the new way at once. The new way is linear motors on all 3 linear axes, optical glass scales, a symmetric H-shaped column with a low center of gravity, and a thermal distortion stabilizing system unique to the company. The old way is craftsman, because the XY table is finished by hand until Yazda considers it infinitely square and infinitely straight, a claim no instrument on the shop floor can falsify. The certified numbers are severe. Positioning accuracy per axis of 0.5, 0.6, and 0.4 microns in X, Y, and Z, positioning under the Japanese JIS standard of 0.1 microns, and machining pitch accuracy within 1 micron. Under ISO 230-2, linear positioning and circularity both hold within 1 micron, and the 5-axis version adds a direct drive tilting rotary table with no gears and no backlash, positioning inside 1 arc-second. The in-house spindle turns 40,000 RPM, and with an optional 80,000 RPM air turbine spindle, the YMC430 finishes hardened optical mold cores to a surface roughness between 8 and 14 nanometers. It hard mills steel beyond 60 Rockwell and cuts cemented carbide, the materials that define mold making's upper limit, and it grinds on the same table, so a hardened core can be milled and jig ground without ever coming out of its clamps. A machine that mills hardened tool steel to a near mirror finish, to 1/10 of a micron in a factory setting, would top most rankings. Here, 5 machines still stand above it. Number 5. The Kern Micro HD. Kern's engineers solved the oldest problem in machine motion, the fact that sliding surfaces stick and rolling surfaces vibrate, by making sure nothing in the micro HD touches at all. The axes ride on Kern's micro-gap hydrostatics, thin films of pressurized fluid that carry the load with no friction, no wear, and heavy damping, a technology carried over from ultra-precision grinding. 5 separate temperature control circuits hold the machine's fluids and structure to within 1/4 degree Celsius. The spindle delivers 15 kilowatts at 42,000 RPM on an HSK40 interface, with options reaching 50,000 RPM, and the newer HD Plus version extends the hydrostatics into the B and C rotary axes, so all 5 axes ride on fluid. The payoff is form and position tolerances of plus or minus 1 micron, not once, but with process reliability, shift after shift, in serial production. The machine also jig grinds and mills in a single clamping, holding parallelism and angularity to 2 microns across combined operations. The proof hangs in orbit. Through the contract manufacturer SEMEC, micro HD machines cut optical housings for TSAT Spacecom laser communication terminals, satellite hardware with lens seats parallel within 2 microns, and series-produced features under 1 micron. Satellites now talk to each other through beams of light aligned by this machine's geometry. Micro HD machines also cut components for First Light Fusion, the British company firing projectiles into fuel targets in pursuit of inertial fusion, where a target machined out of round simply fails to implode correctly. And Kern was not finished. Number 4. The Kern Pyramid Nano. At WLR Precision Engineers in the north of England, a Pyramid Nano drilled 5 consecutive holes through a single human hair, about 0.09 millimeters wide, as a demonstration of what plus or minus 0.3 microns of positioning actually means. That figure comes from the German VDI 3441 standard, measured as positioning scatter, and it makes the Pyramid Nano the most tightly specified machining center Kern sells. Hydrostatic fluid films carry both the guideways and the drive screws, so the machine borrows its motion system from precision grinding while cutting at 1 g of acceleration and 30 meters per minute of feed. The portal frame is cast from a mineral composite Kern calls armorith, shaped symmetrically so heat that does enter spreads evenly instead of twisting the geometry. Spindle runout is guaranteed below 1 micron. The smallest programmable travel increment is 0.1 microns, and finished surfaces reach a roughness of 0.05 microns. Watchmakers run Pyramid Nanos on main plates and bridges cut from the nickel-silver alloy CuNi 18 Zn20, the structural skeleton that every wheel and pivot of a mechanical movement hangs from, alongside optics, metering systems, and medical work. 3 machines now remain, and every one of them cuts with diamond. Number 3. The Precitech Freeform 700. Precitech's Freeform 700 series belongs to the diamond machining world, with oil hydrostatic slideways, an air-bearing work spindle, and a structure engineered for thermal stillness, and in its raster milling mode, it becomes one of the most precise milling platforms on Earth. A monocrystalline diamond tool sweeps line after overlapping line across the workpiece, milling freeform optical surfaces that no rotationally symmetric process can produce. Precitech's own published application work shows what that looks like on a real part. A 20mm diameter component, milled with a tool of 0.75mm radius, was finished with a form accuracy of 0.130 microns, peak to valley, and a surface roughness of 4.3 nanometers. No polishing followed, because none was needed. Laser holographic scales feed position back to the control at a resolution of 34 picometers, and at machine level, the platform is specified to form accuracy of 0.125 microns, peak to valley, with best-case surface finish below 1 nanometer. Machines in this class generate the molds behind head-up displays, F-theta laser lenses, progressive eyeglass lenses, and infrared optics, the freeform surfaces that bend light in ways a sphere never could. A form error of 0.13 microns across a part means the finished shape deviates from pure mathematics by roughly 1/1000th of a hair. The two machines above it improve on that, which should not be possible, and yet. Number 2. The Moore Nanotech, 650 FGV3. The Moore name has meant accuracy for the better part of a century. The hand-operated Moore No. 3 jig borer was the benchmark machine of mid-century precision tool-making, the reference against which tool rooms judged themselves, and Moore Nanotechnology Systems of Keene, New Hampshire, carries that lineage into territory the founders could not have measured. The 650 FGV3 is a multi-axis ultra-precision freeform generator, and fitted with its 60,000 revolutions per minute air-bearing milling spindle, it micro-mills aspheric lens arrays and optical structures directly into metal. The numbers stop sounding like machining. Axis straightness of 0.3 microns across full travel in X and Z, with the y-axis holding 0.3 microns through its central 100 millimeters. Work spindle error motion below 12.5 nanometers, axial and radial. A rotary B-axis on oil hydrostatics, positioning within 1 arc-second, and an air-bearing A-axis with error motions of 25 nanometers. Programming resolution of 0.01 nanometers on the linear axis, and position feedback resolving 0.008 nanometers, 8 picometers, a distance smaller than the radius of a single hydrogen atom. Measure that against the machine it replaced. The earlier 350 FG generation read its position in steps of 8.6 nanometers and commanded motion in steps of 10. The current machine improved on that by a factor of roughly 1,000 inside a single product lineage. On its acceptance part, the machine demonstrates form accuracy within 0.15 microns peak to valley and surface finish of 3 nanometers, measured on the same piece of aluminum. MIT Lincoln Laboratory, the Center for Freeform Optics at UNC Charlotte, and the University of Arizona run these machines at the edge of what optics can be manufactured at all. And in 2026, Japan's Shibara machine moved to acquire the company, a measure of exactly what this capability is worth. A machine that senses its own position in picometers has, by any physical definition, run out of room to improve. Which brings us to the machine that found more room anyway. Number 1. The FANUC ROBONANO. FANUC spent a decade developing the ROBONANO before the wider world saw it, and the current milling model, the Alpha NMIA, remains the most extreme milling machine ever offered for sale. Every linear axis and the indexing axis ride on oil hydrostatic bearings, and in FANUC's words, solid friction, the source of backlash and stick slip, is completely eliminated. The work spindle floats on air. A 50,000 revolutions per minute air turbine milling spindle carries the diamond tooling, and an active damping system cancels vibration before it reaches the cut. Then comes the number that defines this entire ranking. The linear axes accept commands in increments of 0.1 nanometers, and the indexing axis in increments of 1 millionth of a degree. An earlier generation, the Alpha 0 IB, already resolved commands at 1 nanometer, and the current machine sharpened that by a factor of 10. The control is FANUC's own 30 IB, driving FANUC's own linear and direct drive motors, which makes the ROBONANO less a product than a statement of what the world's dominant CNC maker can do when it stops compromising. FANUC publishes that command resolution rather than a certified accuracy figure, and the machine's real credential is the metal it leaves behind: free-form optical surfaces and micro-structured molds finished at the nanometer level for optics, watch components, medical devices, and electronics. For years, Japanese export controls kept the ROBONANO inside the country. when number 1 finally crossed the Pacific to the University of Wisconsin, arriving in the laboratory of Professor Sangkee Min as the first of its kind in North America. It came on a renewable 2-year loan, and FANUC's chief executive attended the ribbon cutting in person. A machine tool with a diplomatic escort. In that Wisconsin laboratory, the machine now runs research into micromachining sapphire, a crystal close behind diamond in hardness. To grasp its scale, consider that your fingernails grow about 1 nanometer every second. The ROBONANO's smallest commanded step is 1/10 of that. It does not so much cut metal as negotiate with it, atom by atom, and no milling machine on Earth speaks that language more fluently. 4 machines came close enough to name. Shibara machine, formerly Toshiba machine, builds the ULG and UVM Nano series in Japan, with aerostatic spindles running on porous restrictor air bearings, generating aspheric and freeform optical surfaces, and the company's micro-grooving work sits squarely in this class, even though most of the platform grinds and turns rather than mills. In Britain, the Ultra Precision Institute at Cranfield, founded in 1968, built a compact micro-milling machine for infrared optics and watch components and spun it out commercially, from the same laboratory that produced the Tetraform C, a nano-grinding machine that finishes fused silica below 5 nanometers of roughness. GF Machining's Microlution. 5-axis micromills hold part tolerances tighter than 1 micron in production shops. And the machine that started it all, the manual Moore No. 3 jig borer, achieved its accuracy with hand wheels, verniers, and gauge blocks, in the hands of an operator who had spent 20 years learning to feel 1/10. Everything in this ranking is an attempt to build that operator into the machine. The most precise machines on Earth still begin with a craftsman working metal against a reference surface, the same act toolmakers performed a century ago, now aimed at picometers instead of thousandths. A century of that obsession, oil films in Germany, granite and diamond at Kugler, picometer scales in New Hampshire, has quietly built machines that outperform our ability to even picture their tolerances. The lenses in your pocket, the satellites overhead, the mirrors reading the early universe, all of them pass through these 15 rooms, held at 20 degrees, where the machines run and the doors stay shut.